All right, going live in 3, 2, 1.
Greetings, everyone. Welcome to the Friday Improving Talk session. Today, I am Rayburn. I'm a vice president with Improving out of our Dallas office, and I am here to talk to you about designing the modern distributed system. So we're going to talk a lot about the steps that go into building this and the major things that you need to be thinking about as you start the process of designing a new system. So with that, let's talk first a little bit about what is a distributed system. I mean, I think it's when two or more computers are involved in a process. So it can even happen on one computer if you're sending a request from one process to another, or moving from an on-site box to the cloud, or fanning out across multiple workers. Basically, any time that a singular process and that's involved in all of the memory management, variable assignment, etc., all those benefits we get from being a process, as soon as there are more than one process involved, and then we need to be thinking about these aspects of a distributed system that we're going to talk about today. Because of the fact that there's opportunities for significant challenges to come in. Now, one of the things I'm not going to be talking about today is, is a microservices architecture the right choice for me? If you're asking that question, I direct you straight to our thoughts blog on our Improving website this week, where the incredible Robin Fuentes has a great article all about those sorts of decisions. This talk is going to be at a higher level than that, basically coming in at, if at all, we have multiple computers or multiple processes involved in a system, what are the key things we need to be thinking about? Everything we talk about here today is absolutely relevant to the world of a microservices architecture, and absolutely should be addressed in your microservices architecture. But it's also relevant if you're trying to just do SOAP calls between multiple services or any other sort of interaction system to system. So let's go ahead and move to talking about our agenda for today. Our agenda for today is we're going to talk about the 5 C's of our systems here. We're going to start talking about contracts and how our systems should interact with one another. Then we're going to move from that to communication. How are they interacting with one another? Then coordination. When we have a single business process that multiple of these services need to interact with, how do we coordinate that effort? And then we're going to talk about when things go badly, when things fall down and we need to compensate, how are we going to handle that? And finally, we're going to spend a few minutes talking about correlation and how important it is in a distributed system. So with that, let's first talk about contracts. Now, for years now, decades now actually, we have been talking about the fact that large distributed systems should be built contract first, that it should be first and foremost about the contract you expose to the outside world. This is your service contract. This is how you are going to be consumed by other pieces of the system. Get that right first, and then worry about the implementation details of how you're actually going to do that work. And I absolutely continue to espouse that way of thinking. But we really, at this point, looking in 2021, need to look beyond simply a concept of contracts first and accept something as true. And that is that if you are building a large-scale distributed system in 2021, CQRS is no longer a good idea, it is just a must idea. Now, if you are not familiar with the acronym CQRS, it stands for Command Query Responsibility Segregation. And what this says, in boiled down, is that we need to, when we are designing the contracts of our system, we need to explicitly separate those things which modify the state of our system, which are commands, and those things which query the state of our system, which are queries. So if I'm Amazon and I'm trying to add something to a cart, adding something to a cart is a command because it modifies the state of my system. It moves where inventory is. Then, or at least potentially moves where inventory is. I'm quite certain Amazon doesn't lock things up just because you put them in their cart. But on the other hand, if I'm trying to determine simply how many of a given product do I have on hand, that query is simply a read-only operation. And this is essentially a separation between your read and write operations, but it is critical. Commands, like I said, they modify the state of your system. They modify the truth that is incumbent in your system. But because of that, when we're thinking about a distributed system, most businesses that I talk to about distributed systems view commands as critical pieces of information, and we as such are more likely to move those onto durable forms of communication. You know, saying I need to transfer $200,000 from bank account A to bank account B is a command in the banking world. When that decision has been made that that transaction has to occur, if I then say, but in the middle of doing that, we lose power, it's okay that somebody has to come back in and restart that process, right? Or, oh, hey, I might only be halfway through that process. I might have debited without adding, etc. That becomes a non-starter for business, and that's reasonably so. And this is where recognize that we have a command, recognize that durable communications are much more likely to be necessary here. Now, when you're looking at distributed systems, the other key thing is you are going to want to cut corners and make the decision that commands do not need to be idempotent, which is a big fancy word that essentially means that given the exact same request, a system should only process that request a single time. Now, when you think about this and you start thinking about communication, which we'll get into next, you might be like, oh, I can handle this with a queue. But in reality, this concept, this idempotent concept, cuts through all layers of your system. And that's why we need to talk about it up top. Because you can't simply go, oh, I expect it to be delivered just once. And because I expect that, my system is idempotent. That's not true because we might have exceptions. We might have reprocessing occur. We might have been halfway through processing a message, shut down, come back up. That message was never acknowledged off the queue, and so we'll pull it off again. We need to build a system in a way that it can know on a transaction by transaction basis that it has seen this transaction before. So in the example I give here, if we have a banking system and we're moving $5 from on a transaction number 123 from bank account 8, and we're doing a withdrawal here, then the new balance, once this is processed, should be $95, of course, for bank account 8. But if we receive that exact same request to add transaction 123 again, we should look at that, go, we already have processed transaction 123, and because of that, we don't need to do this debit again. It shouldn't affect the balance. Idempotent is actually a mathematical term. The technical mathematical definition of this is that a function given x should be the same as the function given x given to the function itself. In math, the most common one, that function that people are aware of that functions as an idempotent function, is the absolute value. If you take the absolute value of -2, the absolute value of -2 is 2. Well, if you then say, what is the absolute value of the absolute value of -2? The answer still remains 2. Essentially, calling that function multiple times doesn't change the answer. And that's what we want to be true in our system here. We want contracts that we can tell our consumers, you can count on the fact that my system is idempotent. If you ask me to do the exact same piece of work multiple times, I'll acknowledge your request, but I won't actually do the work multiple times. This is a truly critical piece when we're looking at distributed systems. And it's hardest to do on commands. For commands, we need to think about, for this request, does it have an identifier that I've seen before? For instance, in the example I gave earlier, have we seen that transaction number? Or is there some composite identifier? Is it the particular combination of multiple fields? But you need to know what uniquely defines the command that you're receiving so that you can determine whether or not you've seen it before and not process it a second time. Now, when we then talk about the query side of things, the good news here is idempotency here happens automatically. All we're doing is reading the state of our system. And if we're reading our system state, obviously that does not change our system state, and as such, it's intrinsically idempotent. This is baked into the RESTful structure of verbs, where we view get as the primary query verb in HTTP REST. And as such, we also say that given a given GET request, that is cacheable because of the fact that the same request made again should get us the same results. That sort of performance optimization is huge. And while I don't ever encourage people when they're building large distributed systems to automatically bake in caching, etc., into the system at the initial point of design, having this split, knowing the difference between commands and queries, creates the ability to add those caching layers and other performance optimizations later without affecting the system or without requiring a massive redesign. Making sure that out of the box, your contracts automatically have been built to address and keep CQRS in mind, and that you know explicitly for every endpoint and every message that your system can take, whether or not it is a command or a query, is critical to the scale of your system in the long run. And CQRS came in, and for many years people viewed it as a nice thing to have, but truly I believe in the modern distributed system, it is not a nice thing to have. It is the table stakes of how we have to be designing systems today. So let's talk about communication methods now. let's talk about how the pieces of our system interact with one another. Really, there are so many technologies here, so many queuing technologies, so many networking technologies. It becomes this interesting thing where we are suddenly faced with this huge number of choices, and it's very easy to get lost, especially when you start realizing that so many of these various communication methodologies then layer on excellent messaging and other additive patterns on top, but that simply confuses and muddles the basic conversation about what type of a communication style is your system using. These days, I really view the message type and the message communication structure of your system falling into one of four camps. The first, and the easiest for most people who have come from a web development background to understand, is a transient communication style, the most common of which here is HTTP. HTTP gives us a really good, lightweight communication style. It is very fast on network, requires very little interchange, client to consumer, on what it is, what we're going to be doing. And its real failing at the end of the day is that of the four options that we have out here, it is the only non-durable solution. If we have an in-process HTTP request and we lose power, have to restart, have a failure, etc., that HTTP request is simply gone. There is no permanent record of it. And for things that are more transient in nature, for instance, for most queries in a system, for instance, HTTP is probably more than sufficient. But again, when we start talking about how do I want to communicate my intent of executing a command, if we're talking about that, really we have to be working in a durable structure. If we're not working in some sort of durable communication format where we can recover from communication faults and processing faults elegantly, then things get much more difficult to properly maintain system state. All three of the other structures that we're about to talk about, queued, streamed, and historic, all give us the ability to deal with communication failures. And so I find that those are the three that I tend to lean to when I am trying to decide the communication mechanism for my commands versus my queries. Now, with that, let's talk about the first one, queued solutions. Queues have been with us for years and years and years now. They are the granddaddy of options in this space. And they're still an excellent option today if they meet your needs. A queued solution is essentially, I express my intent to do something in a message and it is delivered to a mailbox. And then those who seek to process those requests can go to that mailbox, that queue, and say, I'd like the first message that has not been processed off that queue. All modern queues will say, sure, here it is, tell me when you're done with it. And because of the fact that they say, tell me when you're done with it, once a consumer has successfully processed that message, they have to call back to the mailbox, say, I have finished processing message number one, and then at that point, the queue will release and delete message number one as successfully processed. Now, if anywhere in that process something goes wrong, if the consumer picks up the message and never gets back to the mailbox, never calls it back saying, I've completed this, at some point, the queue is going to have a timeout and say, okay, clearly the consumer just failed in some way, so this message is now available for consumption again. And that will mean that it gets processed by another consumer. Well, because of this, we also hit some of our first abilities to hit our first ability to run into a situation where a message is double processed. If that message happens to be huge and just take a very long time to process, then the first consumer might not have called back because it's still working on it. Now I get a second consumer doing that same amount of hard work on that same message. Now, if you've built your system to be idempotent, the second consumer is going to be like, oh, actually this work's already been done, and move about its business, not concerned about that, and simply say, yep, this is done, and off it goes. But this gets us into that situation of recognizing that just because you're queued doesn't mean you're protected against idempotency. You need to think through all of these edge cases of interactions and how it's going to work. Now, when we're looking at technologies that fall into this space of what is a queued system, what technologies do this represent? This represents Amazon's MQ, ActiveMQ. By far the most popular in this space right now is RabbitMQ. All of these actually, to a certain degree, support the common standard that has been established for message queues at this point, called AMQP, the Advanced Message Queue Protocol. And really, that does so much for us if you've got a system that supports AMQP to make sure we don't hit a lot of these sharp edges that queues can have. Because it says, hey, when I give you a message, you need to call me back and tell me that you're done. But if you're going to take a long time, call me back and tell me you need more time. And it has established all of these protocols for properly communicating with a queue so that the queue best properly represents the state of where work is in the system. And there are lots of great options here, and queued systems still absolutely are a very solid option. Now, as the popularity of CQRS type structures has grown, as more and more systems, distributed systems that are being built, have thought about their world clearly delineating between command and query, a mindset has grown where they were like, well, why am I publishing a command and then going someplace to record, essentially just record the command, record that update, record that modification, etc. Why is that database actually required when I can simply represent this as a stream of events that have occurred? And out of that mentality has evolved the streamed system. Now, the king in this space is Kafka, though there are other excellent options in Event Store and otherwise, but it truly does say, let's not look at our message as an artifact. Let us look at our message as the actual final persistent record of what has gone on in our system. And as such, when we come in and we say, hey, we have a transaction that's going to remove $5 from that bank account, that transaction, as soon as it has been added to the stream for account 8, saying deduct $5, that action by itself is the preservation and has accomplished this. Now, because of this model, stream systems have an expectation of their consumers that it is up to their consumer to know where they are in the process of reading the stream. Whereas a queue handles the issue of where is the processing up to at the queue server itself. Streams put that back to the client as an expectation. And that is a perfectly reasonable expectation to shift back towards the client, and stream systems work fantastically, in particular when we are in an always connected world, when I can always talk to the correct stream to be able to deal with things. But the realities of our world are sometimes that I'm in an occasionally connected world. I have a mobile device that might not currently have cellular access, and I want them to be able to log a transaction or add data to the system on their device that will, several hours from now or several days from now, be reconnected and brought back to the central server. When we're in those situations, the variant of a stream system that is known as a historic system works much better. A stream system requires a linear line of events. And when you're adding an event, you have to know what the previous event was. Essentially, it is a linked list of data. A historic system acknowledges that at times maintaining the state required to accurately keep a linked list is not possible because of the realities of our world. And because of that, we instead view the system as a whole as being capable of being a graph where a given event may have two children. Now, we need to eventually deal with the merging back of those two branches of data to a common trunk. We still need to eventually bring it all together, but the fact that we can't bring it all together right now is not a reason to not record things. This model is very popular with systems where we have the occasionally connected nature of our world these days at its heart, so mobile applications and the like. And an excellent project to look at in this space is the Janaga project, if you are interested in this concept of a historically modeled system. So the real thing here is there's no one right answer. There is probably the one right answer for your domain, though. So you need to look at the pros and cons of these various forms of communication and select for your system the one that is right for you. If you've got questions, engage the experts. At Improving, we have lots of experts who can help you with these sorts of questions. And we have experts in every single one of these types of communication structures, so we can get you world-class experts to help you make these sorts of decisions and truly get you deep expertise on any of these that you might be working with. Now that we've decided how we're going to communicate, though, now we need to start talking about how we're going to coordinate work. It's all well and good to have one consumer, and that consumer does a piece of work and then returns, but it's so rarely the case in our world. That model of, hey, please go do this work, and that worker just starts chugging along and doing the work, is what I, in this area, call a imperative consumer. And if you're just doing pure mathematical work, or that consumer is just updating a database, then fantastic, easy breezy, go do an imperative consumer, and your coordination effort is basically non-existent. But sometimes we have I need to ask system A for this, system B for this, system C for this, and then once I have those back, I need to make some decisions and make some further requests, and then finally I need to go and make my final record of what I have decided here. Those sorts of things can be viewed in at least two stark ways, and those being, you can look at them as a workflow, or you can look at those workflows instead as state machines. Now, having spent 25 plus years in this industry, watching Microsoft, IBM, Oracle, etc., try to create, spend lots of development effort to try to create the way to make I just draw a flowchart-like diagram of a workflow, and that will be sufficient to represent the current state of my system at all times. And I've seen them all spend and sell amazing products in this space. I'm here to tell you, in my opinion, this is a problem that is best solved with state machines. And I recognize state machines are the more complex way of viewing things. You have to look at the totality of your workflow, decide what states your system goes through, decide how you transition between those states. But once you have that state diagram drawn, it is so much easier for business leaders to understand. It is so much easier for technology leaders to understand that truly this is where I encourage everyone to go. Now, whatever library you're using to help you in the development of these various distributed systems that you're building might have tooling for the workflow model, probably has tooling for the imperative consumer. That's the table stakes. That's what everybody does. But often the question is, do they have an answer for dealing with a state machine-like structure? And I would encourage you, as you're reviewing libraries, ask this question, because if they do not have a good answer for a state machine representation, then that in and of itself might be the reason not to select that library, because we want to select libraries that are going to enable us to build the system the way we want to, not to build a system the way the library wants us to. We want to be in the driver's seat for our business choices here, not be pushed that way because of a technology library. And so really, when it comes to coordination, look for something that enables you to have a state machine-like workflow. In the .NET space, which is my personal background, I will give a shout out to the amazing mass transit library for doing this so remarkably well. Its state machine sagas that they have in their library allow me to do this very, very elegantly when we're talking with business leaders and truly being able to represent my intention in code very tersely, but very succinctly. So definitely something worth looking at if you happen to be in the .NET space like I often am. All right, after coordination, we move on to compensation. It's all well and good to say we've got multiple pieces working, we now know how we're handling our workflows, but then something goes horribly wrong. The putting on your rose-colored glasses and saying, oh, well, I'll write solid code and we'll never hit an exception in my system is simply purely unrealistic. And when we're dealing with how do we compensate from something going wrong, the first thing is that good exception management is not the end of this conversation. I repeat, good exception management is not the end of this conversation. We need to be able to look beyond that, but good exception management are the table stakes of this game. If you are consuming messages off of a queue or a stream, etc., and something goes, let's take a stream because it's a great example. I'm a consumer of a message off of a stream, and I consume the latest message, and then something blows up. If I don't have good exception management, I might not know that I need to walk back one position in the stream because I need to reprocess that position because I had an error while processing it. But if I don't have that baked in to my exception management, I'm going to simply skip anything that looks hard. You know, it'll literally be like the kid who's mowing the backyard and it's like, oh no, getting in and around all the stuff over by the pool equipment is difficult. So I just didn't mow any of that. It's like, that's not an option here. You have to do the whole job. Okay? And so good exception management is a must. We have to be able to make sure that we're properly dealing with exceptions when they arise. Now, properly dealing with it inside of my singular imperative consumer, though, may not be enough. If I'm going to fail to be able to do a thing, I might have had portions of a workflow prior to me that now need to take compensating actions. The classic example of this, again, is transferring money from bank account 1 to bank account 2. If I go and withdraw $10 from bank account 1, and then I go to add $10 to bank account 2 and fail to do that, it is not okay that the add money function itself just properly handles its exception and reports back that it has an exception. Someone has to know that there was a previous step and that the whole workflow did not complete, and so something else has to happen. In this particular case, it's that the $10 that I withdrew needs to be put back into bank account 1. So in that situation, there are patterns that we can use, but a very good pattern to use is one called the routing slip. What a routing slip allows us to do is have a workflow that is dynamic, that can properly let us, on a message-by-message basis, variant the workflow. And yet, when I go to start processing something, so I say, hey, send this to process A because this has to go to A and then to C in this diagram, I can process A, it sends it on to process C. Now, if process C completes, it routes the message accordingly to wherever the slip says to go afterwards. But if the process C fails, it knows to call back to process A and go, I am compensating back this slip. We've had a problem. And then A can look at that. The routing slip receiver on A can go, oh, I need to reverse or compensate for this transaction. Now, some compensation will be automatic. Some compensation will require us to get a human involved. But the ability to step back in and step back through a workflow and go, hey, you might need to compensate back for this, is critical. And routing slip is a critical pattern to get us to a way to handle this. And so finally here, I want to spend some time and talk about correlation. So when we're building a large distributed system and we've got messages flying through all sorts of services, and we've got logs on every one of those services, and data is flying everywhere, it can become really, really difficult to make sure that we can trace what has been going on. And so when you're building a distributed system, building from the get-go to assume that you need correlation to be able to perform tracing is a must. And so what we want to be able to do is when we send out a request, we want that request to be able to include an identifier that relates to that request and all subsequent requests regarding it. And that will allow our consumers of the responses to keep everything straight. But more importantly, it will give you a thread to trace through for your logging and tracing activities. So if a user says, update my last name, and we send that to a service up in our data center, who in turn but that service might be our API gateway. And then from there, we get to our backend for front-end service, our BFF service, who's actually going to do the work, except for the fact that it isn't the user domain service. So now the BFF is going to call our user domain service and say, update last name from Smith to Rayburn. And so then the user domain says, all right, I've done that, returns a success, which returns a success, which returns a success, all the way back to get back to our browser. Now, if anywhere in there later on, I wanted to come back in and say, where did that initial request to modify a user's last name, what pieces of the system were involved in that process? If when the browser itself sends up the request, if there is an identifier associated with that, saying, please do this, and we're going to call this this request with a correlation ID of 123. Then when the API gateway calls the BFF, it says, hey, here's a service request for you, BFF, correlation is 123. And then when the BFF calls the user service, it passes it along and says, here's a request for you, and our correlation ID is 123. And then when the domain service responds, its response is on correlation 123. When that responds to the API gateway, still correlation 123. And when it responds to the browser, still correlation 123. We kept that identifier throughout the entire loop of that communication. This distinguishes it from message identifiers. The message that's passed along is different each step along that way. And so this is not an identifier for the message. This is an identifier for the whole correlation of the request. And what that allows us then is to later come in, find the original request to the API gateway in our logs and go, I care about what did this particular message, what did correlation 123 cause to have happen in my system? And when that happens, I can then go, oh, all right, search all my logs for correlation 123. And at that point, I'll see it in the gateway logs, I'll see it in the BFF logs, I'll see it in the user logs. And everything is perfectly traceable. Sort those by time and you'll see exactly what happened regarding that service request 123. So correlation is a must for being able to look, diagnose, and handle operational problems. And far too many systems get deployed into production before they ever think about this problem. So take it from me, think about correlation at the start. Now, the one thing about correlation that you do need to think about is when is it no longer the same original request? So let's extend our previous metaphor. A request to change the last name of a user comes up, goes through the gateway, goes to the BFF, goes to the user domain. Now the user domain pushes an event out onto a service bus that says, I've changed user A's last name to Rayburn. That message that goes out is not technically a part of the original request that the user did. So there is a way that we have to look at that and go, is sending out to other portions of the system who might want to know that a user's last name was modified, is that actually part of the same correlation? Or are we now starting a new correlation at that point? So oftentimes you will reach a point where you'll go, you want to know something? This action is truly kicking off something new. And if it's kicking off something new, that new thing should have a correlation ID of its own. So in this case, that event that's just meant to notify other pieces of the system at large, I would look at and say, should receive a new correlation ID. And so this results in us now saying all new work here from this point forward becomes a new correlation ID and is unassociated with the original correlation ID. And that's a good thing to do, and it's an important place to make a decision in your design of the system, what types of activities create new correlation IDs. Now, I might still want some traceability there. And to handle that, my favorite thing to do is to not track just one correlation ID. I will include a correlation ID and a parent correlation ID. And so now, in our example, we have the browser sending up to the API gateway with a correlation ID of 123, but no parent because there is no parent. Likewise, the correlation from the API gateway calls the BFF. No parent there, still correlation 123. The BFF calls the user service. Still correlation 123, no parent identifier involved. When the user service notifies the service bus that a user has been modified, it will send out a correlation of 234, but a parent correlation of 123. This will allow me, if I want to later on, to say, all right, I'm tracing 123. I can see everything that was involved with that by searching for correlation ID 123. But if I then want to see the things that it might have spawned in my system, I can search for a parent ID of 123 and see all of the children that might have been spawned. And when I get those things, I can look at those correlation identifiers. And if I wanted to search for grandchildren, I could simply search for those correlation identifiers in parent, and now I get grandchildren, etc. So I get a full ability to see the full history of what's been going on in my system without ever losing track of where it all started, by simply keeping a pointer back one level of correlation identification by knowing who my parent is. And so I generally recommend, as you're looking at doing this, tracking 2 levels of correlation is sufficient to get you all the visibility you could want within the system. Okay, with that, I've talked for a bunch of time, and I'm sure there are some questions. So Justin, do we have any questions that I can address?
I don't have any questions in the queue, but we might give them a minute to write them up real quick.
Sure thing. While if you've got questions, go ahead and write them into the system at the current time. While we're doing that, let me talk about a piece of recommended reading that I have. Several of the diagrams that I shared today come from the wonderful website enterpriseintegrationpatterns.com, which is the web version of the amazing book Enterprise Integration Patterns: Designing, Building, and Deploying Messaging Solutions by Gregor Hope and Bobby Wolf. Hope and Wolf is a must-have resource if you're designing messaging-based systems. These patterns still matter today if you're building RESTful services. They matter today if you're building queued services. They matter if you're building streamed or historic services. This book is a fundamental work for distributed systems as much as the Gang of Four Patterns book is for object-oriented software development. So I would strongly encourage you to go grab this book. It's an amazing work and a must-have on your bookshelf to be able to learn from. And by all means, go check out the website as well at enterpriseintegrationpatterns.com. It is a great resource that I use weekly to be able to communicate with my clients about the systems that they're building. All right, Do we have any questions?
Well, I don't have any questions. Thanks so much, Tim.
All right, so let's talk quickly about some upcoming sessions. Next week, you're going to be hearing from the esteemed Marcus Thunderbet about Power Automate, and then the week after, you're going to hear from Mark Runyon about elevating your career into IT leadership. Both of these gentlemen are great speakers. I have gotten a chance to know Marcus recently as he's taught some of our consultants in Dallas about Power Automate. He is great, and Mark Runyon actually runs the Improving Talk series, so he is also a great guy to listen to. And so join us on August 13th and August 20th, respectively, to hear from these amazing improvers. And with that, I thank you for joining us today. I appreciate your time, and I look forward to talking to you all next week.